9.1 talks about inferences. This chapter 9, inferences for two sample populations. We're dealing with two proportions. Not to worry, it's not as complex as it sounds. Introduction scenario. Think about whether you plan to vote in the next presidential election in 2020. Let's say I split the responses into two groups, females and males. There are two proportions where proportion 1 equal a number. Let's say, I don't know, 78%. Proportion 2, let's say 2%. Question. Is there statistically significant differences? Well, we don't know yet. We do not know yet. So this is what we do. You're given a proportion for females and proportion for males. I'm sorry. This looks really odd. Let's say this is 65%. And I'm not saying which is which. Now, the idea is, well, does that mean they're different? Some could say yes, some could say no. Well, when would you say it's not different? What must the numbers be? So, we don't care what the proportion actually are, because these numbers don't mean much, because it depends on the population. We care about whether they are the same or not. So, this is the idea. In section 9.1, we will only deal with independent samples with qualitative, which means categorical variables. The logic is that, well, this is the idea. If P1 equal P2, then if you subtract the two, wouldn't you get a 0? If I subtract two numbers and I get quantities and get a 0, doesn't that mean that they're the same? So, we will first collect sample proportions from each population. From the first population, we call it P1 hat. From the second population, we call it P2 hat. Voting. We'll get a sample of women that vote, figure out the proportion that says yes, we will vote, get a sample of men, figure out the proportion of the men that they're going to vote. Now, then we will test to see if this is anywhere close to 0 or not. If those are close to 0, then we say those proportions are the same. Men and women vote the same, drive the same, eat the same, whatever it is you're testing. Recall the logic, and the same idea applies. H naught will always say nothing changed. P1 minus P2 equals 0, or P1 minus P2, P1 equal P2. The alternative will say it's different. Either it's less than, greater than, or equal. Well, remember, if those are equal, we fail to reject the null hypothesis. If P1 is bigger than P2, we fail to reject the null hypothesis. Oh, it's already written there. If P1 is less than P2 by a little, we fail to reject, just like we did with the last section. And if they're off by a lot, we reject the null hypothesis. Well, what's a lot? They'll tell you 5%, 1%, 2%. It depends on the problem. So this is the analogy. We would look at the pre-steps to check requirements. The samples are simple, random, and independent. One of them does not depend on the other. This is the other case. You want N1 P1 hat to be bigger than or equal to 5, and N1 Q1 hat to be bigger than or equal to 5. Also, you want N2 P2 hat to be bigger than or equal to 5, and N2 Q2 had to be bigger than or equal to 5. So, the hypothesis testing, there are 3 of them, just like we did before. If we are dealing with equal or not equal, well, this is 2 tails. Left tail, right tail. Another way of writing those, if I move this to the left, P1 minus P2 equals 0, P1 minus P2 does not equal to 0. Here, P1 minus P2 equal to 0. And here, P1 minus P2 is negative. That's how you know it's a left tail. And here, P1 minus P2 equal to 0. That's the null hypothesis. P1 minus P2, if you move this to the left, it will be bigger than 0, positive. That's a right tail. So, the level of significance, alpha, if not given, we use alpha equal 5%. And the choice depends on seriousness of making type 1 error. That's always the case. No big deal. We just either reject the null hypothesis or try to reject it. So, you notice they do that. This right here is going to be from the actual null hypothesis, and that's going to always be 0. P1 hat you're going to find, Q1 hat you're going to find. N1 is the first population, N2 is the second population. The only difference is this P bar. P bar, you take the successes from the first population, you take the successes from the second population, you add them, and you divide them by the sum of the populations. And Q hat will be 1 minus that. I just adjusted the second page. So again, the 2 tail, the 1 tail, left tail, you know, all of these we already know from before. Let's jump to an example. And we're going to do the p-value in the critical region on every problem like we did before. So, writing, okay, so for step 4, you decide what you want, the critical value or the p-value. Again, we're going to do that on every problem. Write a conclusion either rejecting or failing to reject the null hypothesis. That's the whole process. Let's see how this works. An insurance company is concerned that men are more likely to speed than women. In a sample of 500 women, so N1 stands for women, that's 500 of them. 27 have been ticketed for speeding the last year. So P1 hat is 27. I'm sorry, X1 is 27. Right? Versus use green. In a sample of 250 randomly selected men, 26 of them have been ticketed. Well, you could make a lot of arguments. You could say, look, in 500 women, 27 were ticketed. In 250, half of them, almost the same amount of men were ticketed. Of course they speed up. Well, we don't make that call. We're going to use statistics and support or reject based on the null hypothesis. Now, use alpha is 0.05. We need to know that for the p-value and the rejection region. Significant level to test the insurance claim, and this is the claim. So, the null hypothesis is going to say, the null hypothesis is going to claim that there's no difference. Men and women drive the same. They're going to say P1 equals P2, or simply P1 minus P2 is the 0, meaning it's the same. The alternative is going to say, well, P1 is less than P2. They're different. So let's see how this works. Now, when it says test the claim that the percent of women ticketed for speeding is less than. The claim is right there. So if I reject the null hypothesis, I will support the claim. If I fail to reject the null hypothesis, I'll reject the claim. I'll say, that evidence does not support the claim. Now, the test statistics, from what we have before, we need few things. Z equal P1 hat minus P2 hat minus P1 minus P2. Well, this is always going to be 0. Divided by the square root of this P bar, Q bar over N1 plus P bar, Q bar over N2. This I got from the previous page. Let's get a few things out of the way. Well, P1 hat, that is 27 over 500. P2 hat, that is 250 over, that's 26 over 250. So, now I need to find this P bar, that is x1 plus x2 divided by the sum of 500 and 250. Of course, we could plug all of that in a calculator and figure out what those are in decimals, or we could just do it one shot. It's kind of a lot of work, but it's all good. So this turns out to be 0.07, which means Q bar is 1 minus that. That is 0.93. P1 bar turns out to be the blue. The blue turns out to be 0.054, which means Q1 hat will be 1 minus that. If you plug that in a calculator, that's 0.946. And P2 hat, if you plug that in a calculator, that turns out to be 10.4%, which means Q2 hat turns out to be 1 minus that, 89.6%. Now, if I plug all of those in my calculator, the Z will equal, and let me put those, 0.054 minus 0.104 minus, you could put the 0, you could ignore that, over the square root of P is 0.07 times 0.93 divided by N1, which is 500, plus 0.07 times 0.93 divided by 250. Now, if I plug all of this in my calculator, that turns out to be a negative 2.53. Okay, I want to take a bit of time so that I could show you how I got all of these numbers. So if I take 27 divided by 500, there's the 0.054. Again, right away, take 1 minus that answer. I'll get the 946. If I take 26 divided by 250, I'll get 0.014, and again minus the answer. Oops. 0.104 minus 1. The 896, and if I take 27 plus 26 and I divide that by 500 plus 26 plus 250, I'll get the 0.07 minus 1, 0.93. Now if I want to put this in my calculator, I'll use parentheses, 0.054 minus 0.104, that's the top, divided by the square root, and I'm going to input it as I see it. I see parentheses 0.07 times 0.93 divided by 500 plus 0.07 times 0.93 divided by 250, close parentheses, equal negative 2.5299, negative 2.53. I just want to make sure that you see how we get all of that. I'm going to put that in the notes for you. Okay, it froze for a minute. Let me see what's wrong. Come on, work. So now we're going to do the p-value. Well, let's see. The p-value would be, what's the probability that z is less than negative 2.53? Well, I'll get my calculator out. There's negative 2.53, and I'll get that probability to be, and I'll go for, let me enlarge this just a bit. Enlarge the wrong part. And I will go for a distribution, and we're going to go for normal CDF and negative 1.99. The upper is really a negative 2.53, if you remember. And what's the probability? Let me copy that down. What did I do? I messed it all up. There we go. Now I'm in shape. So, what does this tell me? This tells me the probability is 0.57%. That's less than 1%. That almost never happens. What does that mean? Reject the null hypothesis. That's what that means. Based on this, I would reject the null hypothesis. So far so good. So, now let's go for the critical region. The critical region, we will go by, well, they want a 5%. If it's a single-sided, this is 0.05. I need to know the cutoff point. I will go to my calculator again, and I will go for an inverse normal distribution. I want the area to be 0.05. I want a left. That cutoff point is negative 1.64. Negative 1.64. So I look at the test statistics. Isn't this number to the left of that, assuming that's a 0? It falls in the rejection region. What's the conclusion? Reject the null hypothesis. So what's the conclusion? Well, reject the null hypothesis. This is the null hypothesis, and you rejected it, and the claim was right there. In conclusion, you would say, as we expected, there is enough sample significant evidence to support the claim, and once you get to the claim part, you pretty much reiterate this part, word for word. That the percent of women ticketed true percentage of women ticketed for speeding is less than the percent of men. And the reason it's very important for you to say enough sample, because based on this sample, they only ask 250. Did they ask the people? Should they have asked 500 of each? Anyways, beyond the point. The point is, based on this sample, we support or not support. In this case, we don't.